Okay, so remember back in Calc 1, we had a rule called the power rule for antiderivatives. So we had the antiderivative of x to the n dx what was the antiderivative of x to the n? You added 1 to your power, so you had x to the n plus 1. And you divide by your new power. Plus c, very good. Plus c. And that rule worked almost all the time, but it doesn't work for one number. What number is the bad number? N equals. It works as long as n is not the number -1. What's wrong with the number -1? You would end up with 0 on the bottom, and that rule didn't work. All right, so here's the first thing we're going to do in Calc 2. We're going to fix that. We're going to define an antiderivative of x to the -1. So we define ln of x, and ln stands for natural log, equals the integral from 1 to x of 1 over t dt. All right, so that's a very strange definition. We're defining a function in terms of an integral. So for example, if I asked you to find the ln of 3, what would you tell me the ln of 3 is? Integral from 1 to 3 of 1 over t dt. And then you would have to evaluate that integral. This is the same as the integral from 1 to 3 of t to the -1 dt. So we can't use our power rule to evaluate this integral because we have a -1 power there. We can't add 1 to our power and divide by a new power. So how could we evaluate that integral? Or at least how could we approximate that integral? All right, well, what do integrals mean again? In terms of a graph? It's the area under the curve. So if I graph the curve 1 over t, the curve 1 over t looks something like this. Oh, no, it doesn't. Forget that. That's not what the graph of 1 over t looks like. What's the graph of 1 over t look like? I do it upside down and backward. The graph of 1 over t looks like this. And I forgot a little rule here, an important little rule. X has to be a positive number. Back up there. All right, so here's the graph of 1 over t. And I would go from 1 to 3. And so that integral that we're talking about would be that area. How could I estimate that area? I could use Riemann sums. I could use rectangles. What else could I use? I could use the trapezoidal rule, or I could use Simpson's rule. So I could approximate it. I could get a very accurate answer, but I can't find the exact value. How come I can't find the exact value? What kind of number is it? It's an irrational number. So it's one of those decimals that goes forever, never repeats, never terminates. No pattern to it, really. All right, so that's our definition of ln. Then we're going to have a whole bunch of properties of natural log. Some of these I'll prove, some of them I won't. All right, so number 1, again, I'm going to write down the definition. The definition is ln of x is the integral from 1 to x of 1 over t dt. And x has to be a positive number. So that's the first property. The first property is just the definition. Property number 2. ln of 1 equals 0. Can anybody tell me why ln of 1 has to be the number 0?
Because your start and end point is the same.
My start and end point would be the same. ln of 1 would be the integral from 1 to 1 of 1 over t dt. And this was one of our properties of integrals from Calc 1. What happens when your lower bound and your upper bound are exactly the same? The integral is 0. All right, property number 3. If x is bigger than 1, ln x is positive. And conversely, if x is smaller than 1, but it still has to be bigger than 0, ln of x is negative. All right, so can anybody tell me why, if x is a positive number, ln of x is bigger than 0? Like a minute ago, we looked at ln of 3. How do I know ln of 3 is a positive number? Edward? 3 is to the right of 1, that's true. And what was ln 3 again? ln of 3 was that area. Isn't that area a positive number? Yeah, there's nothing really special about 3, is there? Go ahead.
Is the reason because there's a vertical asymptote at 0 for the function 1 over t?
Well, there is a vertical asymptote at 0, that's true. But that really doesn't have anything to do with that being positive. We'll see for a minute. That vertical asymptote does have to do with something. And we'll see that in a minute. But the reason, if we pick a number bigger than 1, and I want the ln of 3, for example, the ln of 3 is this area, and that area is positive, isn't it? Because it's up above the axis. So that's why if x is a number bigger than 1, the ln is positive. Now what if x is a number smaller than 1? Like what if x is a half? According to what I wrote here, if x is a number smaller than 1, I'm claiming that the ln is negative. So I'm going to claim that ln of a half is a negative number. Can anybody tell me why it has to be negative? Well, what would ln of 1/2 be by the definition? It would be the integral from 1's always on bottom, 1/2, 1 over t dt. So again, in a picture, here's my 1 over t function. And I'm going from 1/2 to 1, so I'm looking at this area. But I said the answer was supposed to be negative. Doesn't that area look positive? I'm going from 1 to 1/2. I'm going backward, aren't I? Notice I have the big number on bottom and the small number on top. And we had a rule about that in Calc 1. Usually we want the little number on bottom and the big number on top. What was the rule about switching the numbers? It makes it negative. So this is negative the integral from 1/2 to 1 of 1 over t dt. This area that I drew, I tried to trick you. This area that I drew is the area from 1/2 to 1, not the inner area from 1 to 1/2. So in order to flip my bounds of integration, I've got to add a negative sign in there. So ln of 1/2 is a negative number. I don't know what number it is, but I know it's negative. Questions on that?
Why is 1 a base? Why are we using 1 as, I don't know, why is 1 a big number? Why does 1 have to be a big number? Or is that just because you made it that number?
Our definition says we always start with the 1 on bottom.
Anytime for 1.
Anytime we want to define ln, ln is the integral from 1 to x. It's always the number 1 on bottom. The truth is you could start with any number on bottom, but then everything would shift. And what I mean by that is if I went from 2 to x, then I would have to say ln of 2 is the number 0, because then I would go from 2 to 2. And then that's not our traditional ln. Our traditional ln from pre-calculus and algebra and things that you learn, ln of 1 is always the number 0. So that's why we define it to have the number 1 there. Okay? All right, property number 3. Oh, property number 4. I did number 3. I claim that ln of x is always increasing. How in Calc 1 did we show that functions were increasing? We took the first derivative. So if f of x equals ln of x, which is the integral from 1 to x of 1 over t dt, for x bigger than 0, then what's its derivative? All right, so everybody always remembers the fundamental theorem of calculus part 1. People almost always forget the fundamental theorem of calculus part 2. Fundamental theorem of calculus part 2 said, if we had a function defined in terms of an integral, then what's its derivative? No, it's not the area under the curve. It's the function inside. It's the integrand. It's called the integrand. Integral, integrand. So what's the derivative of ln x? Not 1 over t, 1 over x. What ends up happening is the derivative and the antiderivative, they're inverses, they cancel each other out. So all that's left is the function, but we're using the letter x. So the derivative of ln x is the function 1 over x. And if x is always positive, and that's our definition, x has to be positive, is our derivative positive? Yes. So since our derivative is positive, the function is increasing. All right, so we actually did something very important there. Not only did we show that the function is increasing, but we also learned what the derivative of ln x is. So that one was kind of a bonus property as we were working. Property number 5, the derivative of ln x is 1 over x. And then I'm going to throw in property number 6. What if I didn't have just the letter x inside of my ln? What if I had some other sort of function? Then how would I take the derivative?
1 over the function.
Close. It would be 1 over the function times the derivative of the function. Where'd that come from? That's the chain rule. It's just like when you had the derivative of sine. The derivative of sine x was cosine x. What happened as soon as we put something else inside of that sine? The sine of x squared. What did we have to do? The derivative of sine of x squared was cosine x squared times 2x. All right, same thing happens here. The derivative of ln takes 1 over whatever's inside there. So the derivative of ln of g of x is 1 over whatever's inside there. But then we have to use the chain rule, and we have to multiply by the derivative of the inside. All right, so an example. F of x is the ln of 9x cubed. What's the derivative?
All over 9x cubed
1 over 9x cubed. When you have an ln, it's always 1 over whatever's there
times 27x squared.
times its derivative, times 27x squared.
Would it be incorrect to write that as 9x to the negative 3?
Yes. Why is that incorrect to write it as 9x to the negative 3? It's almost correct. Because 9x to the negative 3 would be 9 over x cubed. So you got to do something to push that 9 down to the bottom also.
So the quantity of, wouldn't make sense to do that.
It wouldn't make sense with a quantity either, because then you'd have to cube the 9. So that would be a bad thing, wouldn't it? You don't want to do that. So no, you can't write it as 9x to the negative 3. I don't know why you would want to do this, but you could write it as 9 to the negative 1 x to the negative 3. That would work, but that looks more complicated to me than just writing it as a fraction. Now, of course, we could simplify. We could take 27 and divide it by 9. 27 divided by 9 is 3, and x squared divided by x cubed over x. So again, I mentioned this before, but the nice thing about using WebAssign is I'm pretty sure WebAssign will take that as a correct answer. It doesn't force you to simplify. And I'm pretty sure WebAssign would take that as a correct answer too. Okay? Questions on that? All right, a few more properties here. Number 7. I already showed that ln of x is increasing. Now I'm going to claim that ln of x is concave down. Always. Never concave up. Always concave down. How in Calc 1 did we show that functions were concave down? We took the second derivative. All right, so if f of x is ln x, we already figured out the first derivative. The first derivative was 1 over x. So what's the second derivative? What's the derivative of 1 over x? Close. No. Negative 1 over x squared. Think of this as being x to the negative 1. So you'd have to bring the negative 1 down and then subtract 1 from your power. It would be negative 1x to the negative 2, which is negative 1 over x squared. So how does that prove that my ln function is concave down? The second derivative is always negative, isn't it? If the second derivative is negative, our function is concave down. Questions on that? All right, number 8. LNs have lots of properties. If f of x is ln x, the domain is x is bigger than 0, and the range is all real numbers. Okay, so why is the domain x is bigger than 0? What's that? Yes, because there's a vertical asymptote there, and that's why when we define our ln of x, back in our definition of ln x, how did we define the domain? X is bigger than 0. And how come we didn't want to go past x equals 0? That's because of that vertical asymptote right there. Can we plug 0 into this 1 over t function? No, we can't. So that's why we didn't want to use 0, and that's why we didn't want to use any negative numbers. We didn't want to cross that vertical asymptote. All right, so the domain is easy. Now, how do you convince me that the range is all real numbers? Well, can you get 0 for a y value? Yeah, how did we get 0? ln of what gives you 0? ln of 1. So we can definitely get 0. Can you get positive numbers? Yeah, how'd you get positive numbers? Well, what kind of numbers do we plug in for x? Not positive. Bigger than 1. Okay, so for example, we looked at ln of 3. ln of 3, that was a positive number. But I'm claiming I can get any positive number. I'm claiming I can get, if I plug in the right number, I'm claiming I can get ln of something to be 5,000. Are you convinced of that? That I can get a big number like 5,000 to be my y number? How would I do that? I would have to pick a very large x number. The bigger x number that I pick, the more area I'm going to keep adding under this graph, aren't I? So if I want to get a y value of like 5,000, I don't know exactly which number I'd have to plug in. Pretty big number. I do know what number I have to plug in, actually. Do you know what number you'd have to plug in to get 5,000? No? We'll talk about that. But I could do it, couldn't I? I could keep plugging in bigger and bigger numbers, adding more and more area until I got my area to be up to 5,000. I could make it work. How about negative numbers? How could I get like negative 257? I got to plug in numbers closer and closer to 0, don't I? And then we would get the area over here, but as we saw, we have to flip our bounds so we get negative numbers. So that's not really an exact proof, but it's convincing, I think, that my range, I could get any positive number, I could get any negative number that I wanted to. All right, rule number 9. Here's one that you might remember from your pre-calculus days.